Okay, last time we were considering the emitter follower. Circuit, which, if you recall, with a current source bias, looks like this. We've got two transistors. The top one is called the emitter follower transistor, QEF, and the collector of that transistor is tied up to the positive power supply, which we'll call VCC, typically in the context of bipolar circuits. And the input voltage comes in on the base. The emitter voltage is the output, and that's also the collector of our bias transistor, Q bias. And then the bias voltage, V bias, is down here. The bias transistor's job is to set up a current, which we would like to be a constant current, ideally, flowing in the transistor QEF. And we found that if we assumed some things about the transistors, namely that they matched each other, they were operating at the same temperature, and we also assumed that they were idealized in the sense that beta goes to infinity, so there's no base current, and the collector current is exactly equal to the emitter current, and that there is no early effect. What we found was, so beta goes to infinity, alpha goes to 1, and VA goes to infinity. Under those assumptions, we found that Vout was equal to Vin minus V bias, and that was true for Vin greater than or equal to V bias plus VCE sat. Okay, so that's what we found last time. And what we'd like to do this time is to go back and put in gradually remove some of these idealizations. So the first one we're going to think about is what happens when we let beta be finite so that alpha is not equal to 1. And then we're going to go and input in a finite early voltage, and we'll see how each of these things complicates the picture. Okay, for this particular circuit, it will turn out that they don't complicate the picture too much, but we'll see how that works. I should mention also that this is called an emitter follower because the emitter, which is the output, follows what the input is doing with a shift of V bias. So for an NPN bipolar transistor based emitter follower, we have that the output voltage is V bias less than the input voltage. So if the input voltage goes up, the output voltage, which is the emitter, follows what the input voltage does. And so that's the origin of the name. This is sometimes also called a common collector amplifier. That's another name for this circuit. I don't find that name to be particularly enlightening. It's part of a standard taxonomy of single transistor amplifiers made with bipolar transistors, but the name emitter follower is so much more descriptive of what the circuit does that I tend to almost forget that it's called a common collector amplifier. Okay, so the first thing we're going to do is let beta be less than infinity. So alpha is approximately 1, but alpha is less than 1. So for typical beta, which is like about 100, alpha, which is equal to beta over 1 plus beta, would be about 100 over 101, which is maybe about 0.99. Okay, so that would be a fairly realistic scenario. Well, how does that affect our picture? Well, what that means is that the emitter current of QEF is I bias by KCl, and that means the collector current here is going to be alpha times I bias. All right, so you remember before what we did was that for Q bias, the forward active model implied that I bias was equal to IS e to the V bias over UT. Call that equation 1. Now for QEF, the forward active region model implied that alpha I bias is equal to IS e to the V in minus V out over UT. That's equation 2. And so, the only difference here that we have is that now the collector current flowing in QEF is alpha times our I bias. And so we can still take the ratio. So if we take 1 divided by 2, we find here that on the left-hand side we have I bias divided by alpha I bias. Okay, the I biases go away and we're left with 1 over alpha is equal to IS e to the V bias over UT divided by IS e to the V in minus V out over UT. So the IS's go away, and this is equal to E to the V bias minus V in minus V out over UT. Okay, that's pretty terrible. Let's see if I can clean that up a little bit. V bias minus V in minus V out over UT. Not much better, but so we have on the left-hand side 1 over alpha. On the right-hand side we have E to the V bias minus V in plus V out over UT. We take the log of both sides and we multiply by UT. We get UT log 1 over alpha is equal to V bias minus V in plus V out. And if you like, there's a property of logs that says log of x to the y is y log x. 1 over alpha is just alpha to the minus 1, so we can rewrite this as minus UT log alpha. We can move all the stuff that's not V out to the one side of the equation, and we have V out is equal to V in minus V bias minus UT times the natural log of alpha. And so, from the standpoint of the voltage transfer characteristic, the only way that a finite beta comes in makes alpha not equal to 1, and so we have a slight shift in the characteristic downward from what we had before by this amount, UT times the natural log of alpha. Now UT at room temperature is 25 millivolts, and alpha, let's say alpha is about 0.99 typically. So log 1 plus x is approximately x for small x. So log of alpha, where alpha is 0.99, will be minus 0.01. Okay? So we're talking about ut, so minus ut log alpha is approximately going to be, so the minus and the minus cancel, so we have plus 1/100th of 25 millivolts, which is about 0.25 millivolts, or 250 microvolts. Okay? So we're talking about a shift in this characteristic. It looks like it's in the positive direction by about 250 microvolts. That's a pretty small shift. Okay, so you can see that our picture of what's going on can be corrected for this less than idealized assumption, finite beta. And in this particular case, it doesn't shift things by too much. It basically just takes the curve that we had before and moves it up by about 1/4 of a millivolt. Okay? So that's the finite beta. That's how finite beta comes into the picture. Okay? So let's let beta be finite and also have a finite early effect. So let's let beta be less than infinity and VA be less than infinity. Okay, so in this case, we're going to have a similar thing, only we're going to use our exponential model for the early effect. Okay, so for Q bias, the forward active model implies that I bias now equals IS e to the V bias over UT plus V out over VA. Okay, so here's the term that we had before, and we multiply by our factor e to the V out over VA to model the early effect. For QEF, the forward active model implies that alpha I bias is equal to IS e to the VBE, which is V in minus V out, over UT plus VCC minus V out over VA. Okay, so that's the collector to emitter voltage of QEF. And so this is now our new equation 1, new equation 2. We do 1 divided by 2. And that implies on the left-hand side we're going to have 1 over alpha. The IS's will cancel. We're going to have an e to the V bias over UT plus V out over VA. And then downstairs we have e to the V in minus V out over UT plus VCC minus V out over VA. Okay, so we canceled the IS's and we canceled the I biases. And now we can write, if you like, we can take a couple of steps into account here, where we take the log of both sides minus log alpha on the left-hand side. So we took the log of both sides and we took the 1 over alpha and we changed that into minus log alpha. And on the right hand side we're going to have basically just the argument of this exponential minus the argument of this exponential. So it's going to be V bias over UT plus V out over VA minus V in minus V out over UT minus VCC minus V out over VA. And so now we're going to do what we did before, which was multiply everything through by UT, and that's going to give us minus UT log alpha equal to V bias minus V in plus V out. That's basically this term and these two terms. And then we have some other terms. So we've got we've got this term involving V out, this term involving V out. So we have plus 2, and it's going to be UT over VA times V out. So that's 1, and then we have plus V out over VA from this last term. So we collect those up, there's 2 of them. And then we've got this term involving VCC. So that's going to be minus UT over VA times VCC. And so now we want to collect up all of the V out terms. So we have 2 of those, can factor that out, and we have V out times quantity 1 plus 2 UT over VA. And then on the other side of the equation, we're going to have our V in minus V bias. We're going to have our UT log alpha. Right, so if we move that to this side, we have a minus UT log alpha. And then we have this other term here, which we move to the other side, we get plus UT over VA times VCC. And of course we can divide both sides by this factor 1 plus 2 UT over VA. And maybe I'm going to erase this stuff up here. To continue on. And that tells us that V out is equal to one over 1 plus 2 UT over VA times V in minus V bias minus UT log alpha over the same 1 plus 2 UT over VA. And then we have this other term, which is plus UT over VA over 1 plus 2 UT over VA times VCC. Okay, so this is getting a little more complicated. Let's think about this. What is UT over VA? Right, so UT at room temperature is about 25 millivolts. Right, that's KT over Q. It's about a 40th of a volt. VA for a typical BJT might be on the order of 25 volts. That would be a typical number for the early voltage. And so UT over VA would be equal to roughly 1 over 1,000. So 25 millivolts divided by 25 volts would be 1/1000th, so 10 to the minus 3. So whereas before we had Vin minus V bias without any kind of gain factor other than 1 here, here we're changing the gain by to 1 over 1 plus 2 UT over VA, which is roughly 1 over 1.002, which would be about 0.998. So 1 over 1 plus 2 VA, or 2 UT over VA is about 0.998. And so this thing which we had decided before was minus UT log alpha was about plus 250 microvolts. That would be very close to what it was before. And also we have this notion that we now have a power supply dependence. So now, whereas before the power supply voltage didn't come in at all, now there's a component of V out that is due to the power supply, but the power supply, the gain on the power supply is going to be basically 10 to the minus 3 over 1.002, which is basically 0.00998. So UT over VA over 1 plus 2 UT over VA is about 0.00. So shift the decimal point over 3 places. 0.998. So the gain on the power supply is very, very small, roughly 0.1%, or 1 millivolt per volt. The gain on the input voltage is very, very close to 1, about 0.2% away, 0.998, very close to 1. And the offset due to the finite beta and the fact that alpha is not equal to 1 would again be just about what it was before. Okay, so that's an idea of kind of this, of progressively adding in what we might call second order effects, non-idealities in the transistor, and seeing how they perturb what we learn about the circuit when we first meet it with our idealized assumptions. We'll be doing this type of thing, at least in broad brushstrokes, kind of an outline form, for most of the circuits we meet this semester. We'll be starting out with some idealized assumptions, trying to understand how the circuit works, trying to get to know the circuit. And then we're going to now go back and say, now what would happen if we were to add in finite base currents or finite beta? And what would happen if we added the early effect in? And how would that change our picture? And this is a very important principle of developing an intuition for how a circuit works. And so we're going to hopefully model it for you several times so that you can develop those skills for yourself. But this circuit is actually quite a useful circuit. We'll see it pop up in slightly more complicated circuits. And it turns out to be a very nice first example because it is a circuit that's amenable to a large signal analysis in ways that a lot of other circuits that we'll see just aren't. So anyway, that's it for this particular segment. We'll see you next time.